are in Chapter 7, which has been on principal stresses in beams and stresses under combined loads. This is the 55th session overall and the 4th session in Chapter 7. Here we discuss examples on combined load cases. So we look at a number of examples on rectangular sections and one example on rectangular hollow section, I-beam, helical spring, and dam problem each. These are the sessions covered in the first 4 chapters. When it comes to loading cases, we dealt with axial loads, torsion, and bending. These are the sessions covered in chapter 5 and 6. When it comes to loading cases, we dealt with shear and thin-walled pressure vessels. We also discussed transformation of stresses and strains in chapter 6 and failure theories. We are now in chapter 7. In session 55, we are dealing with combination stress case examples. In the next session, we carry out a brief summary of discussion till chapter 7. This is a case of a rectangular section subjected to moment and shear. So here we have a rectangular section and this wire is in tension. So there are forces acting at A and B. We are required to find out the stresses in small a, b, and c. To start with, we find the length of AB. Once we have the length of AB, we find the component of this force in the vertical and the horizontal direction. The vertical force is considered to act to the center. So we can see that this section will be subjected to a moment, shear, and compression. We have found out the horizontal force, so multiplying by this distance, we get the moment acting. The moment will cause a compressive stress at C and a tensile stress at A. So we find out the values of the tensile stress and the compressive stress. This vertical force will cause compressive stress in A, B, and C. So this is the vertical force and we find out the value of the compressive stress. At A, we subtract to get the tensile stress. At B, there's only the compressive stresses acting. And at C, we add to get the overall compressive stress. There's no shear stress at A and C, so we find out the shear stress acting at B. We use the force in the horizontal direction to find out the shear stress acting at B. Here we have another rectangular section subjected to moment and shear. A force of 15 kN acts as shown. This angle is 40 degrees and here we have a roller support. This force is resolved in the longitudinal direction and in the perpendicular direction to it. Since this is a roller support, the reaction at A will be horizontal. We resolve the reaction at B to a force in the longitudinal direction and perpendicular to it. To start with, we take moment about B. Then this force and RA will cause moment about P. So this force multiplied by 8P will be equal to Ra into this vertical distance. So we get Ra. Next we take moment about A. Then this force and Rpx are the forces causing moment, from which we get Rpx. This angle is 50 degrees, so Ra cos 50 plus this force will be equal to Rpy, from which we get Rpy. We can consider the equilibrium of this bottom portion to find out the stresses acting at A, B, and C. Rpy causes compressive stress at A, B, and C. Rpx will cause bending stress at A and C. Rpx will also cause shear stress at B. So using the value of Rpy, we first find the compressive stress. Rpx into this distance gives the moment, and we find the tensile stress at A and the compressive stress due to bending at C. At A, the normal stress due to bending and compression gets subtracted. So we get this value of stress. At C, the normal stress, which is compressive due to bending, and the stress due to compression both get added and we get this stress. At B, using Rpx, we get the shear stress. The normal stress acting at B is this compressive stress. We have a rectangular section which is subjected to tension, bending, and shear. We are required to find out the stresses at M, N, O, and P. M is at the midpoint of the section, and P also is at the midpoint. N is equidistant from O, which is at the edge, and from M. This force only causes tension. This force causes bending about the y-axis and horizontal shear. So this is horizontal shear. This is the bending moment about the y-axis. This force causes vertical shear and bending moment about the z-axis. So this is the vertical shear and the bending moment about the z-axis. We find out the normal stresses and the shear stresses separately. So we first find out the stresses due to the tensile load. All the 4 points are subjected to the stress due to the tensile load. This vertical load causes bending stresses at M, N, and O. So we find the bending stress, which is positive. This load causes bending stresses at O, N, and P. The stress at O and N are positive, and the point P is subjected to compressive stress. Due to this load, there is shear stress at M and N. Q is found out using these two diagrams. Due to this vertical load, there is shear stress at P. Point M is subjected to tensile stress and stress due to moment about the z-axis. So we add them up. This is the shear stress. Point N is subjected to tensile stress, stress due to moment about y-axis, and stress due to moment about z-axis. So all these three gets added, give the total stress, and we determine the shear stress as well. Point O is subjected to tensile stress, stress due to moment about y-axis, stress due to moment about z-axis. So these three gets added up. Point O being at the corner is not subjected to any shear stress. Point B is subjected to tensile stress and compressive stress due to moment about y-axis. So we get the net stress here. Also, this is the shear stress. Structure of a rectangular section to which these two loads are applied. We'll find out the stresses acting at the points P, M, and N at the bottom. We'll also find out the principal stresses acting at P, M, as well as the maximum and minimum shear stresses. This force is resolved into a horizontal force along the x-axis and a vertical force. The horizontal force causes a shear along the x direction and also a moment about the z-axis. So this moment. The vertical force causes a compressive force and also a moment about the z direction. This force causes a shear along the z direction and a moment about the x-axis. A section is taken at the bottom and it is shown here. Due to the horizontal force in the x direction, we get this shear and part of this moment. Due to this vertical force, we get this compressive force and also part of this moment. Due to this force, we get the shear along the z direction and this moment about the x-axis. We first find out the compressive stress, which is applicable to all 3 points. Then we find the stresses at the point P. It will be subjected to compressive stresses due to both these moments. Will also be subjected to shear stress due to the 60 kilonewton load. Here we have added up the compressive stress due to the compressive force and due to bending. The point N is subjected to tensile stress due to bending about the x-axis. It is also subjected to shear stress due to this shear force. The point M is subjected to bending stress due to moment about the z-axis and also about the x-axis. As we can see from the arrows, both causes compressive stress. We add the compressive stress due to the compressive force to get the total normal stress acting at point M. This point is at the corner, the shear stress is 0. So at M, this stress and 0 are the principal stresses. These are the stresses acting on the element at point P. plot the stresses on the right-hand face as A and the stresses on the top face as B. We can find the diameter, and as such we can draw the whole Mohs circle. We can find the value of the principal stresses which are given here. From the Mohr diagram, we can see that if we rotate this element by 6.0 degrees in the anti-clockwise direction, then it will be subjected to only the principal stresses. The Mohs circle also gives the maximum and minimum shear stresses acting at P. We have a rectangular section with a load acting on the edge as shown. At the base, this load will cause a shear force, a moment, and a torque. We have taken a section at A, and these are the forces that will act on the section. So this is the shear force, this is the torque, and this is the moment. Since A is at midpoint, it will not be subjected to any bending stresses due to the moment. We first find out the shear stress that will act at A due to the shear force. So we use VQ by IP, and this is the shear stress obtained. For this rectangular portion, this is the smaller dimension and this is the larger dimension. The maximum shear stress due to torque occurs at the midpoint of the larger side. So it would occur at the point A. We can find out this maximum shear stress using this table and the formula. To start with, we find P by C, which is 1.5. Now for 1.5, alpha is 0.231. So we substitute the torque and alpha in this equation as well as B and C. So to get the maximum shear stress at, which is also the shear stress at A. The direction of the shear stress due to the shear force and due to the torque are the same at A, so they get added up. So this is the element at A with the shear stresses acting. If we rotate the element by 45 degrees, then we'll have only the principal stresses acting on the element. Here we have a structure that has a hollow rectangular section. It is subjected to a force as shown. At any given perpendicular section, the section will be subjected to shear, torque, and bending. The maximum stress will be at the base. We are required to find out the stresses acting at N. N will not be subjected to any stress due to shear. So it will be subjected to stress due to bending and due to torque. Here we have considered a section at the base. The moment acting at the base is 35 kilonewton into this distance. So this is the moment. The point N will be subjected to tensile stress, and we find out the stress that will act at N. The torque acting on the section is this force into this distance. These are the outer dimensions of this rectangular hollow section. The thickness is 10 millimeter. So we find the dimension of the center line. Shear stress is equal to torque divided by 2 into area within the center line into P. So we can find the shear stress. For an element at N, these are the stresses acting. We plot this right hand face as A in the Mohs circle and the stresses acting on this top face as B. Then join AB and form the Mohs circle. So we get the principal stresses acting. Principal stresses are given here. You can find the maximum and minimum shear stress from the Mohs circle. If we rotate by 8.88 degrees in the clockwise direction, then the element will only be subjected to principal stress. Here we have an I section subjected to loads. This is the designation of the section. These are the dimensions. We are given the area IYY and IZZ, where this is the YY axis and this is the ZZ axis. We are required to find out the stresses at the base at point 1, which is 96 millimeter from the edge. This force in the vertical direction will cause shear and it will also cause a moment. So this is the shear and this is the moment which will be about the z-axis. The section here is shown in this figure, and due to the vertical load, this is the shear and this is the moment about the z-axis. The horizontal load will cause a shear and a moment about the y-axis. So this is the shear and this is the moment about the y-axis. And it is shown in this diagram. This is the shear and this is the moment about the y-axis. To find out the bending stresses for moment about the z-axis and the y-axis. About the z-axis, the moment is due to this 45 kilonewton load. So this is the moment. Y is half of t and Iz is Izz given here. So we find the stress. This is the moment about the y-axis. So to find the bending stress, we use the moment. Now BF, which is the length of this flange, is 264, so half of it is 132. So 132 minus 96, so this is 36. So for Z here we have used 36. IY is substituted here. So we get the stress at 1 due to moment about the y-axis. As we can see from this figure, this stress will be negative, while the stress about the z-axis is positive. So at the point 1, this is the net bending stress, which is tensile. We now find the shear stress. We first find the shear stress due to this horizontal load. So Q here has to be found for this shaded portion. whose length is 96 millimeter. This total distance is 132 millimeter. We find the distance of the centroid of the shaded portion to be 84 millimeter. The thickness of the flange is 31.8 millimeter. So Q is given as 96 into 31.8 into 84. We use IY from here, and B is the thickness of the flange, which is 31.8. So we get this value of the shear stress. Here we find the shear stress due to this vertical load. For that, we need the Q of this shaded area. This distance is 96. The thickness of the flange is 31.8. And this is the distance of the center of the flange from the ZZ axis. We use I, ZZ, and B again is 31.8. So we find out the stress, the shear stress. Here we find out the direction of the shear force due to the two loads. We first look at the direction of the shear force due to the 45 kilonewton load. If we consider section AA, then this 45 kilonewton load will cause tensile stress at the top of the I section, where the point 1 is located. Here a section at AA is shown. As we move away from the 45 kilonewton load, the moment will be higher and the tensile stresses will be higher. So the tensile stresses on the right will be greater than the tensile stresses on the left. This is the point 1, and this shaded area has been shown here. Here again the tensile stresses on the right are greater than the tensile stresses on the left. So this would be the direction of the shear stress. Let us now look at the direction of the shear stress due to the 65 kilonewton load. At the far end of this I section, the 65 kilonewton load will cause compressive stresses. So at the point 1, there will be compressive stresses. Here, this diagram has been rotated. So this is the point 1. A section again is taken at AA. This shaded portion is the portion corresponding to in this diagram. The stresses on both sides are compressive. The magnitude of the compressive stresses on the right side will be larger than the magnitude of the compressive stresses on the left side. This portion has been shown here isolated. Here again the compressive stress on the right side are larger than the left side. So this would be the direction of the shear stress on the underside or on the section BCED. So this is the underside here is BCED. So the direction of the shear stresses in these two cases are opposite. So these are the shear stresses acting on element 1. The shear stress gets subtracted. We earlier found out the tensile stress. The stresses on this side are plotted here, and the stresses on the top side are plotted here. With the diameter known, we can form the Mohs circle and get the principal stresses, which are given here. From the Mohs circle, we can also find the maximum shear stress and the minimum shear stress. If this element is rotated by 19.6 degrees in the clockwise direction, then it will be subjected only to principal stress. We earlier discussed the forces acting on a dam. Here we find the dimension B, or the thickness required at the bottom of the dam. The height of the dam is taken as 1.5 meter. To find B, we consider that the dam is filled to the brim. So the height of water is also 1.5 meter. The density of the concrete is taken as 2300 kg per meter cube, and the density of water was 1020 kg per meter cube. This is the value of G used. This diagram shows the forces acting on the face of the dam. Unit width is considered. Here H is due to the pressure of the water and W is due to the weight of concrete. They create a moment about the center. The distance from the center are given here. So this is the moment acting at O. Using this value of rho and rho GH, we find this capital H as 5H dash square, where H dash is in meter. And W, the weight here, is H1 BU divided by 2. So we get this expression of moment. There will be also a compressive stress acting due to W, and it is given by H1Q into P divided by 2 divided by P into 1. So we get this expression. We obtained the moment. So this is the bending stress at the dam face, where the distance is minus B by 2. We add the compressive stress to get the total stress at the dam face. Concrete cannot be subjected to tension, so the stress at the dam face at the bottom here has to be 0. In this expression, both H1 and H dash are 1.5 because this dam is filled to the brim. We are given the density of concrete, and using mg, we find out the load acting per meter cube. Substituting stress at the dam face as 0, and with H dash and H as 1.5, we get E as 1 meter. We earlier discussed a helical spring and derived formulas for maximum shear stress and deflection of a helical spring. Here, this radius T and the number of coils is given, where also given the allowable shear stress, and G. Tau max is given by this formula. Here we do not know F, we know tau max. RC is 25, so we find out the maximum force that can be applied. With the force determined, we can find out the deflection. Here N is the number of coils. So substituting values, we get delta.